In this video, we explain the concept of switch transformers. Using these transformers, you can scale up your deep learning model by any arbitrary number of experts while keeping the model's complexity constant. For example, you can build a model with a huge number of parameters yet keeping the model's complexity low. Each of these experts can be a different large language models like ChatGPT, Llama, or others. Hence, you can benefit from all of them without increasing your training or inference time. To understand switch transformer, we first need to understand regular transformers. In modern large language models such as ChatGPT, the input text is processed by an encoder to get a latent representation, which is then fed to a decoder to get an output word. Both the encoder and decoder are designed based on several transformer layers. This diagram shows a transformer. The main component of a transformer layer is a MultiHead attention module or simply an attention mechanism, which we are going to explain it in this video. Using this module, the model can relate each word in the input text with others. To understand the attention mechanism, we first talk about a simple indexing task. Consider a book in which each page can be considered as a key. When you have a question or query, you need to find the most relevant pages or keys to find your answer. The retrieved information can be considered as a value, which can come from a combination of various pages or keys. In this paper, Attention is All You Need, which was published in 2017, the authors proposed the self-attention mechanism, which can be considered as an indexing task. As mentioned in this paper, using this mechanism, we can find the relationship of one word with other words in an input text. To compute self-attention, we first compute a query, a key, and a value for each word in the input text to get three matrices, Q, K, and V. If you have 10 words, then each of these matrices will have 10 rows, and the columns represents the latent features. To do a similarity check and find the most relevant keys based on the query, we use a dot product. This produces a new matrix. We then scale the numbers in this new matrix and apply the softmax operations to normalize the numbers in the scaled matrix. This creates a normalized matrix that can be considered as an attention map. Finally, we multiply the attention map with the value matrix to retrieve our information. The retrieved information contains the relation of each word with respect to other words in the input text. Now, let's see how we can compute the query, key, and value matrices. Consider a sample text like this one. The first step is to split the text into smaller chunks or tokens. For example, we can consider each word as a token. We then pass each token to an embedding layer to convert it to a vector of numbers. Each embedding vector can be considered as a numeral representation of the related token. In the original transformer model, the length of the embedding vectors is 512. The embedding vector of each token is then multiplied by 3 different trainable matrices to get one query, one key, and one value for each token. We can consider these 3 matrices as feature extractors. In order to implement the self-attention mechanism, we have 5 steps. In step 1, we put the embedding vector of each word in one row of a matrix. For example, if we have 2 tokens and the length of our embedding vector is 4, then we obtain a matrix of size 2 by 4. This matrix is then multiplied by a weight matrix to get a query matrix. For example, the query vector of the first token will be in the first row of the query matrix and so on. We repeat the same process to get one key matrix as well as one value matrix for our input text. In step 2, we compute the similarity between the query matrix and the key matrix. This can be done by multiplying the query matrix by the transpose of the key matrix. This gives us a similarity matrix. For example, the second element in the first row of this matrix shows the similarity or relationship between the first and second word. In step 3, we scale the computed similarity matrix by dividing it by the square root of dk. dk is the number of columns of the key matrix. This prevents the dot products from becoming too large or too small. In fact, it helps to stabilize the gradients during training and improves the overall performance of the model. The next step is step 4. In this step, we apply a softmax function to the scaled similarity matrix to normalize the values within it. This allows us to obtain the weights on the values. In fact, this matrix can be considered as the attention weight matrix. We use this matrix in step 5 to retrieve our information from the value matrix using a weighted average. Specifically, we multiply this matrix by the value matrix to get an output matrix called A. Each row in this matrix is a new embedding of the relevant word which captures not only the semantic meaning of that word, but also the interaction of that word with other words. Note that the dimension of matrix A is the same as the input matrix. For example, if the embedding of each word is of length 512, you will get a new embedding of the same size as the output. Now, let's see what is the multi-head self-attention mechanism. If you feed the input data to multiple independent self-attention layers and concatenate their output embeddings, you can build a multi-head self-attention layer. Each of these independent layers are called a head, and you can train them independently and in parallel. This allows to expand the capacity of our network as each of these heads can attend to different parts of the text. This was a short introduction of the multi-head attention mechanism. We now go to the next part of this video. In the first part of this video, we talked about the main component of the transformer layers, which was the multi-head self-attention mechanism. Another important component is the FFN layer, which is a feed-forward neural network. The purpose of this layer is to introduce nonlinearity to the model and capture complex patterns in the data. It consists of two linear transformations with a nonlinear activation function applied in between. As we discussed earlier, the embeddings of the input tokens are first fed through the multi-head attention layer to get a new embedding out of them that captures the relation between different tokens. In the next step, the new embedding are passed to the FFN layer. The FFN layer then computes another embedding or representation that can be passed to the next layer. In fact, you can consider the FFN layer as a translator that transforms its input representation to another representation that can be used for the next transformer layer. Note that in a transformer, we can connect several transformer layers to increase its capacity. These layers are connected together serially. In the original transformer, we have 6 transformer layers. However, if we increase the number of layers, the complexity of the model increases significantly. But, is there any way to increase the capacity of the model without changing its complexity? In this paper, which was published in 2022, the authors introduced the concept of switch transformers to answer this question. In fact, a switch transformer can have a much more capacity of the original transformer, but with almost the same complexity as them. In a switch transformer, the conventional FFN layer is replaced by a switching FFN layer, which we will explain it next. The initial operations of a switch transformer is similar to a regular transformer. For each input, we first get the output embedding of the multi-head attention mechanism for it. However, instead of passing the computed output to a FFN layer, we pass it to a router. Router itself is a trainable neural network. Also, instead of having one FFN layer, we can have any arbitrary number of such layers. These layers can be considered as independent experts. For each of these experts, the router computes a probability for sending the computed embedding to it. In this example, the router sends the new embedding to the third expert as it has the highest probability. After getting the output of this expert, we multiply it by the computed probability to scale it based on the router's confidence. Now, if we change the input, this time, the router may decide to route the data to another expert. In fact, using this switching mechanism, we can use a different expert based on the input sequence. For example, consider that expert 1 is a large language model that is trained on mathematics, expert 2 is on chemistry, and expert 3 on physics. Now, based on the input data, the router can adaptively select the best model to do a task, such as question answering. Note that, since the router always uses only one or a few number of these experts, the complexity of the switch transformer is always constant. However, we can ideally have any arbitrary number of experts. This was a short introduction about the switch transformers. Hope you like it. Please don't forget to like and subscribe our channel.